Hello, I'm David Walton, and welcome to our talk introducing our paper, Metameric Varifocal Holograms. I'll first briefly introduce computer-generated holography, or CGH. Holograms are images generated by the interference of light. They generally use light from a coherent laser light source. In computer-generated holography, a common setup uses a phase-only spatial light modulator. This is a device which applies a different phase offset to the light incident upon it at each pixel. This light then propagates through the air and interferes at the target plane to produce the desired image or light field. CGH is an exciting display technology as it's capable of reproducing truly 3D output. However, there are some practical challenges involved in displaying images via CGH. First, the relationship between the target image to be displayed and the SLM phase map used to generate it is complex. Generally, phase values must be found by an iterative process such as Gerchberg-Saxton or gradient descent optimization. Secondly, the SLM has a limited resolution, much like a conventional display. Partly due to this, it might not be possible to reproduce an output exactly. This is particularly challenging when light field output is desired, but even in a 2D case such as the simulated example shown, the optimized holograms may suffer from artifacts. Our goal in this work is to explore how gaze information can be exploited to improve the perceived quality of CGH. Gaze information provides two critical pieces of information for us. Firstly, it tells us which pieces of the hologram will fall into the user's fovea and which will be in their peripheral vision. We exploit this using a perceptual loss function, the Metameric loss. Secondly, it allows us to infer the user's current focal depth. We exploit this by generating varifocal holograms at the user's current focal plane. First, to introduce the Metameric loss, we'll briefly introduce the concept of metamers. Two different stimuli are metamers if they're perceived as identical, despite the fact that they might actually be different. Here we're focused on ventral metamers as introduced by Freeman and Simoncelli. These occur due to pooling in the human visual system. This effect causes us to only perceive local statistics of oriented features within pooling regions of our visual field, roughly speaking local texture. These pooling regions grow with eccentricity. As a result, images like the one on the right can appear correct when fixating at the correct location, the red dot, even though in the periphery only local texture is being matched. The goal of our Metameric loss is that any metamer to a target image should have a low loss value. In this way we can allow artifacts such as noise or ringing in our outputs as long as those artifacts cannot be perceived. This expands the space of solutions and can allow for convergence to results that are perceptually closer to the target, even if they may actually be further away under losses such as mean squared error. Briefly, our loss function uses a many-to-one perception function which models pooling given the current gaze location. To compute a loss value, we apply the perceptual function to the current image I and the target image T. The loss is then computed in the perceptual space. Perceptually similar images map to nearby points in this space, resulting in low loss values. For more detail on the perception function, please see our paper. The Metameric loss code is also available on GitHub. Now I'll discuss the accommodation aspect of our approach. Our intuition here is that given a user's gaze location, it is typically possible to infer their accommodation based on the depth of the scene point they're looking at. Given this focal depth, we can render content or capture real content with the appropriate focal depth, and depth of field matching the human eye. We then optimize the hologram to match this target just at the user's focal plane. Our optimization pipeline is implemented in PyTorch. The parameter to optimize is the phase map displayed on the spatial light modulator. Our forward pass consists of modeling the light transport, including the modulation by the SLM, light propagation, and computing the amplitude of the light at the focal plane. We then compute the loss relative to the target using our Metameric loss function. Since our light transport model and loss are fully differentiable, we can make use of PyTorch's automatic differentiation and optimization code to estimate the phase map. Please see our paper for more details, and the source code for this is also available on GitHub. We also test our pipeline on a real holographic display. Looking at this image, following the light path from the laser visible on the left, the laser light is first focused into a collimated beam by the first lens, and then linearly polarized. The polarized beam is reflected by a beam splitter, and then reflects from the SLM, its phase being modulated in the process. The modulated light passes through the beam splitter again, and then through a focusing lens and aperture before being captured by a bare camera sensor. We first show some example simulated results using our pipeline. Here the gaze location is the keyboard at the bottom left of the image. We compare against mean squared error, loss, as well as baseline foveated losses, and to optimizing the image to directly match a metamer to the image under MSE. Our metameric loss produces a higher quality foveal region than MSE, and in contrast to the baseline foveated approaches, has perceptually correct content in the periphery, without blur or disturbing high-frequency content. We also test our holograms on the real prototype display. Here we compare our target rendered images, simulated results, and real captures from the display. The captured results are very similar to the simulated results, although the real captures suffer from some additional noise due to model mismatch. We believe our approach can take advantage of improvements in optical modeling to provide even better results in the future. Thank you very much for your attention. Please see our paper for more detail on our approach. The source code for hologram optimization, target rendering, optimal simulation, and the metameric loss are all available on GitHub via the links provided.